Okay, let's finish this example from last time.
I'll take questions. Okay, so we're trying to find all the critical values, and then go on to finding the extrema of this function, natural log of x plus 1 minus tangent inverse of x. So we found where the domain ends. We found where the derivative was undefined, and then we have to find where the derivative is equal to 0. Okay, so the domain ended at -1, so -1 was a critical value. The function was undefined at -1 as well, so we get to keep it as a critical value. And then when we find where this is 0, I get x is equal to 1 or x is equal to 0, so 0 and 1 are both critical values as well. And then we have to test if they're extrema or not. And we put in 1/2. Put in 1/2, right? And we get a negative out. So between 1/2 and 0, it's going to be negative in there. We're going to put in -1/2 and put in -1/2. I get 1 minus 1/2 plus 1 minus 1 over -1/2 squared plus 1. And that time is going to be 2 minus 4/5, which is positive. It's going to be positive, negative here, positive there. So I do get a critical value at 0. What type of critical value is it? Is it a maximum or a minimum? It's a maximum. Why is it a maximum? Yeah, it's got positive slope here, negative slope here, so it hits a max, right? It goes up until it goes down. Okay. And then let's put in a test value of 2. We're going to calculate dy dx at x equals 2. 1 over 2 plus 1 minus 1 over 2 squared plus 1 is 1/3 minus 1/5, which is still positive, right? 1/3 is bigger than a fifth. Okay, so I get another critical value because it goes from negative to positive. I get another extrema there. I have a minimum there, right? So we have a max at x equals 0, which is equal to f of 0, natural log of 0 plus 1. Is it minus the arctangent? Yeah, minus the arctangent. Of x. This is equal to, well, the natural log of 1 is 0. The arctangent of 0 is 0. It's going to hit a maximum of 0 at x equals 0. Okay. And it's going to have a minimum at, what do we say, 1. Natural log of, well, at x equals 1. Which is f of 1, natural log of 1 plus 1 minus the arctangent of 1, which is the natural log of 2 minus the arctangent of 1 is pi over 4. This is about, well, negative 0.69 minus what was that, like 0.797? Yeah, 79, 78 something. About -1.5. And it starts being positive again. Okay, so questions about that? You guys looked at homework stuff? Do you have homework questions? Some of those? Yeah, which homework? Anybody? Yeah, Matt? There should be. Does it just give you 0? Undefined? Let's look at that. So oh, okay. Because it's not in the original domain of the function, you can't use it. Does that make sense? It can't be a maximum or minimum for the function because the function is not defined there, which is sort of weird. We get to throw it out right away. That's the problem with how the book kind of defines things sometimes. It's not perfectly precise, but I would still call it a critical value, but it can't be a maximum or minimum. But that, I guess they're taking it as it can't be a critical value because it's not in the domain. Is that helpful? Yeah. There's just little technicalities that I would sort of gloss over at this point, but the computer system doesn't let you. So if you think you're running across one of those technicality things, let me know and we'll talk about it. Does anybody want to do this one while we're got it open? Yeah. Okay. So critical values, X values for all critical points. So we check where the endpoints of the domain are. And the domain is -infinity to 4, union 4 to infinity. So 4 is a possible, we'll call it a possible critical value, critical point. There might even be a difference between critical point and critical value in the book. I don't know. But x equals 4 is not in the domain. So it's not. Okay. And then we're going to check where the we take the derivative, f prime of x. Well, I got a quotient rule going on, so I got to go x minus 4 times 2x minus x squared times 1 over x minus 4 squared. That's just my quotient rule. Okay. And then if I expand that out, I get 2x squared minus an x squared minus 8x over x minus 4 squared. So that's going to be 2x, just x squared. X squared minus 8x over x minus 4 squared. So f prime is undefined at x equals 4, but we already eliminated that one. F prime is 0 at x equals 0 and x equals 8. So it probably wants It wants 0 and 8. Yeah. Okay. Other homework questions you guys have? Yeah. That's fine. It's not that simple. What is the absolute maximum minimum of the given function on the interval? So select the correct choice below if necessary and fill in the answers. Okay, so it is a closed interval that's bounded, right? It's closed 2, 7 is the interval. So there definitely will be one. So we're going to have to pick A for sure. I just have to figure out what it is, right? Okay. And so endpoints of the interval, possible critical values, or critical points. Is that what it's doing? Critical points, whatever. We've got 2 and 7 because those are the endpoints of my domain. Okay. I have to look at f prime, which is equal to minus 6x squared plus 54x minus 108, right? That's defined everywhere, so I don't have any place where the first derivative is undefined. So defined always. So no domain issues. Okay, and then I need to set this equal to 0. First thing I do if I'm solving this is I'm going to divide everything by -6. So 0 equals x squared minus 9x and 14. No. 18. 18. And that means that I've got x minus 3, x minus 6. So I've got 4 possible points I have to look at. I have to look at 2, 7, 3, and 6. Right? Those are my possible critical values. And I want the absolute max or the min, so I'm just going to plug in all 4. Hang on. Let's do just a little bit more so that I don't actually have to plug in all 4, and we'll do it a little easier. So the function f prime is -6 times x minus 3 times x minus 6, right? That's what f prime of x was. Okay. So if I plug in a point that's between 2 and 3, I want to know if f prime is negative or positive. So I know I have a negative from the -6. If I take a number in here and I subtract 3, I have a negative from that, right? From this factor. And if I take a number in between here and I subtract 6, I get another negative, right? So I get 3 negatives. So the derivative on that interval will be negative. Good with that? On this interval, I get the negative from the -6 again, but if I plug in a number between 6 and 3 into the x minus 3, I get a positive, so that factor is positive. If I plug in a number between 3 and 6 into the -6 bit, I get another negative again, so that one's positive. Okay. And then between 6 and 7, I have the negative, but then I have a positive and a positive. So this one's going to be negative again. So of these 4 possible critical values, of the 4 critical values that we've got, critical points, which ones are minimums? Yeah, I've got a minimum here and a minimum here. Okay. Because this one, it's going down to here, up to here, down to here again. So this will be at a low point, and this will be at a low point. So I'm just going to check 3 and 7 against each other to see which one's the smallest. Okay, so f of 3 is minus 2 times 27 plus 27 times 9 minus 4 times 27 times 3. I'm going to do it that way so I can factor out a 27. So it's going to be 27 times -2 plus 9 minus 12, which is going to be a negative. What is that? 7? No, minus 5. Minus 135. Yeah. Okay. And f of 7 isn't going to be as easy to calculate. Minus 2, 7 cubed is, I think, 243. No, that's 8 cubed. That's 3 to the 343. Yep. And then 27 times 49 and minus 108 times 7. 50 times 27 would be that, and then I want to take away one of the 27s, and then that is going to be minus 756. These are going to be kind of close, aren't they? Okay. 1323 minus 686. $636 minus 756. It's a negative 119. Is that what you guys all get? Anybody do this on a calculator? Okay, I think the absolute min is that one. I don't think that one's not quite as low. So we'll try it. And hopefully my arithmetic's good. Minus 135 at x equals 3. No? Okay. Let's pull out a calculator. It is asking for a maximum. Thanks. Okay, so we do the same thing, only we do the maximum value. So we're going to look at 2 and 6, and that was a lot of arithmetic for nothing. Maybe it asks us for the minimum later, but probably not. Okay, so at 2 and at 6, we're just going to use a calculator this time. I didn't even put it in the right function because it's 54, isn't it? Not 27. Minus 108. See if we'll can handle that. Yeah, 92. 92 for that one. Is that the right function? No, it's still not the right function. Okay. Why did I think there was a 54 there? Did I calculate? Did I move this wrong? Oh, the 54 was in the derivative. Okay. $27. And the 108 was multiplied by an x, wasn't it? Was there a constant on the end? Okay. Minus 2x cubed plus 27x minus 108x. Okay. Add x equals 2. Minus 124. That doesn't seem very big. Okay. And then we'll do this at 6. This should be probably positive here. Nope, minus 108. There's our function. It looks like, yeah, we do hit a minimum there at 3 if I graph this thing. At 2, I do have kind of a maximum there on the graph, right? It doesn't go up any farther there, right? And it comes down, hits a minimum at 3, goes back up, hits a maximum at 6, and then at 7, it's going to be another minimum again right there. Yeah. It doesn't look like it changes much on this version of the graph, but so our maximum is that's the biggest one. So we'll plug that one in. Minus 108 at x equals 6. Try that. Okay, we're happy with the maximum rather than the minimum. Ah, good, we already did this. So this was minus 135. Did I do that calculation right? We'll see. At x equals 3. Okay, I did do that calculation right. Yeah. gonna look like this. Of those choices, I think that's the one that we pick. I haven't seen the fourth one, but yeah, okay. So we have a maximum at 2, we have a minimum at 3, we have a maximum at 6, we have a minimum at 7. That's what we'd stated, so that looks right. Okay. Questions on that one? Other questions you guys want to talk about? Yeah. So how we do this with the algebra type stuff, or what it even means? Okay, so you've got this function, and it's given as a function of time. G is a constant, S is meters, and T is in seconds, right? So the height of a moving body at a certain time. Which of the following expressions gives the maximum height of the body? So none of these have T in it, so you're kind of thinking originally that S and T are my variables. G's in this thing, so I think of it as a constant. V naught's a constant, S naught's a constant. Okay. And so we want to find out where this is hitting a maximum, so we can take the derivative, set it equal to 0, and figure out what time it hits the maximum, and then plug that time back into the function to get the maximum height. Does that make sense? So ds dt, that's going to be gt with a minus sign on it, plus v naught. That's what the derivative is. So this is equal to 0 when v naught equals gt, or when t equals v naught over g, right? Okay, so the height is s at v naught g is going to be minus 1/2 g v naught over g squared plus v naught over g plus s naught, which is equal to, one of those g's cancels, right? And I get a v naught, so I get a minus 1/2 v naught squared g plus v naught squared g plus s naught. So I've taken away half of v naught over g, v naught squared over g, and I've added a full one. So that's just v naught squared over 2g plus s naught. So I go with that one. So it's just solving this problem, but there's no specific numbers in there. Other thoughts on this one, or other questions? Anybody online have questions? I'll just work some more homework questions from the book. Okay. Critical points. It wants critical points. We want to find all critical points here for this function. What should we do? Take a first derivative. Okay, I can use a product rule and a chain rule. So I will think of this as the product of those two things. And so it's the first times the derivative of the second, which is that times 1, right? Plus the second times the derivative of the first. Which is that. So this looks like, well, it looks like I can factor out an x minus 1 times an x minus 3. And then what's left over in the first bit is a 2x minus 1. And what's left over in the second bit is a 2x minus 3. So this looks like x minus 1, x minus 3 times 4x minus 2 and minus, oops, that should be there, right? A 4x and a minus 6 and a minus 2 is a minus 8. So G prime equals 0 at x equals 1, 2, and 3. Those are my critical values. Okay. Sometimes resisting the temptation to FOIL things out helps, right? So we gotta kind of be careful what you're doing there. Factor out some stuff. Does it have any other critical values? What didn't we test? All we did was find where the derivative was 0. What else should you check when you're looking for critical values? If it's undefined or endpoints of domains, right? But we didn't have any endpoints for domains here. And this is a polynomial, so it's defined everywhere, right? So we don't have to actually check those in this case. So just write that down. Defined everywhere. And no endpoints for domains. Okay. Find another one. Find abs max min of. Let's go g of x equals e to the minus x squared on negative 2 to 1. What should we do here? First derivative. So I get a chain rule. E to the minus x squared again times the derivative of the inside bit, which is minus 2x. Okay, so that's going to be equal to 0 when e to the minus x squared equals 0 or minus 2x equals 0. So x equals 0. This is never true. So that's a critical value. That's the only one from the derivative being 0. We also have to check what endpoints. So x equals -2, x equals 1, x equals 0. So far, 3 things to check. And is the derivative or is the function undefined anywhere? No. We'll just say that the function and the derivative are defined on the entire interval. Okay, so we want to find absolute maxes and mins. So let's check these 3 points. We'll put them into the function g of -2, e to the -4 times, nope, that's it, right? It's just e to the -x², e to the -4. Okay. G of 0 is e to the 0, which is 1. And g of 1 is e to the -1, which is 1 over e to the 4th. So this is the biggest. Why is that the biggest? Yeah, because the denominator is 1, right? It's got the smallest denominator out of all this stuff. This has the biggest denominator, so it's going to be the smallest. Good. Okay. Graph this thing kind of looks bell curve-ish. Biggest there at 1. Then at 1 we were there, and at 2 we're here. Probably comes down faster than that. It goes up to the middle and down to the other side. You guys remember odds and even functions? So you get an odd function, f of x, that has a local maximum at x equals c. What can you say about x equals -c? Yeah. Local minimum. Odd functions, remember, have origin symmetry. So you rotate it around the origin. So if you have a function that looks kind of like this, and at c you have a local maximum, then if you rotate it around here at -c, you'll have a local minimum. Propeller shaped, basically. What if it was an even function? It'd be a local maximum still. Even functions have symmetry across the y-axis, right? Um, what if your function doesn't have any critical points or any endpoints to its domain? Can it have a maximum? Can it have a minimum? What's a function like this look like? Yeah, straight line's a good example. Domain's everything, no critical values. Does it have any maxes or mins? So you can have functions that don't have any maximums or minimums. If you have a differentiable function, the only place that you can have max and mins are critical points or endpoints of domains. So this is a pretty good test for pretty much any function that you're going to come across. If the function's not continuous, then all bets are off, kind of thing, right? Because every single point could be a maximum or a minimum. So that just makes things hard, right? If you have this function that just bounces around everywhere, it's discontinuous, but it's defined everywhere, you have no idea what you're going to get. Any other questions on 4.1 stuff? Yeah. So I think I just use critical value as my term, and the book uses critical point as its term. I'm using it sort of interchangeably. Their definition for critical point is an interior point of the domain, so it has to be in the domain. Okay. Of the function where f prime is 0 or undefined. Okay. And so you get the 0 points and you get the undefined bits on the endpoints of closed intervals, because it has to be inside the domain. It has to be a closed interval to include the endpoints. That's pretty good definition, actually. Yeah, and it goes critical point value is what the output at the critical point is. So the critical value must be the output if we're going to go technical there, I guess. I always like to say critical value because it just means it means the x coordinate or the y coordinate, but a point to me means it's somewhere in space. Does that help? Okay. Okay, let's talk about 4.2 stuff a little bit. So we'll just do a little start on 4.2. No, that's not what I want. Okay, so 4.2 is the mean value theorem. And we'll just talk a little generally about what the mean value theorem says. So the mean value theorem, well, I have a mean and I have a value and I have a theorem, right? So what's the mean of a anything? What's a mean? Average. Means average. So this is an average value theorem. So if I have a function, something like this, and I'm starting here at time equals 1, and I'm ending at, say, time equals 5. Right. I always get confused with the mean value theorem, and I think they apply it with integrals too, but they call it slightly different, but they mean the same thing. Yeah. Okay. So to me, the mean value theorem would be like, if I took all of these values and I figured out, I added them up and I found the middle, it'd be somewhere in there. Does that make sense? But that's not what this one is. That's the integral version of the mean value theorem. Okay, so this one, oops. All right, so this one says, if I start here and I end here, and I have a differentiable function, this is more about average rate of change. So here's my tangent line. Right. If I start here and I end here, if I never go at least this fast and at most this fast, then I can't get from here to here, right? If I always go too fast, I'll end up up top, right? If I never go exactly that slope, I would end up too high. If I never go exactly that slope, if I always go slower than that slope, I'd go too low, right? And so what the mean value theorem here says is there's always some point on this curve that has a tangent line which runs parallel to that secant line, right? So there is always a tangent line that runs parallel to the secant line between the endpoints. Okay. And so let's write that out mathematically as a theorem. So theorem. And this one's called Rolle's theorem. No, this is not called Rolle's theorem. This is called the mean value theorem. we'll use Rolle's theorem to prove it. Rolle's theorem is kind of a specific case that generalizes, but okay, so if f is a differentiable function on the interval AB, continuous at A and continuous at B. Let me go differentiable on the interior and continuous at A and B. So it's going to be continuous on the entire thing because it's differentiable on the interior and continuous on the endpoints. It's continuous everywhere. Then there exists C inside that interval, AB, the interior, with f prime at C equal to f of B minus f of A over B minus A, right? The slope of the tangent line at C is equal to the slope of that secant line. That's what this says. Okay. Rolle's theorem is a special case. Says if f of A equals f of B equals 0, and f is continuous on the closed interval, differentiable on the interior, then there is some point in AB, say C, with f prime at C equal to 0. So it's a special case where your endpoints are on the same level. Right. I don't even need this to equal 0, actually. I just need f of A to equal f of B, right? Yeah. Okay, that just says if you start at some point and you come back to that point and you did it in a continuous way, there's some place where you had to have been flat. Maybe you were flat in more than one spot, but you had to be flat at least one place, right? Here and here, if you're level, you're going to be level at some point. And that's pretty much it. That's Rolle's theorem and the mean value theorem. We've got a corollary. If f prime is 0 everywhere on the interior, then the function has to be constant because it can't go up or down, right? Otherwise, there'd be a secant line that you'd have to match the slope to, and if it was never not 0, then you couldn't match that slope. Okay. And then you get the corollary if, so let's do those. If f prime at x equals 0 for all x in AB, then, and let's say, and f is continuous on AB, then f is constant on AB. Okay, proof. If not, then there would be a secant line with non-zero slope. And that would break rolls down, right? Okay. And that's basically the whole proof. Okay. And then this corollary is kind of nice. This one's actually really nice. If f and g are continuous on AB and f prime equals g prime on the interior AB, then f equals g plus some constant. What does that say geometrically? So here's f, and we know that the derivative of f is the same thing as the derivative of g. So the direction you're going at any point in time for f is the same as the direction you're going for g at any point in time. So if you go up for f and then you go down and you go up, you have to go up and down and up for g, right? And if the derivatives are exactly the same, then any change in direction happens at exactly the same time and all that stuff. So the only way that you can be different is if you start at different points. But then when you start at different points and you follow the same direction, your change at any time has been the exact same amount. So the difference between here and here and the difference between here and here is the exact same, right? So you basically just get parallel where this difference is always a constant. Right. That's how that, you can't change it all. And that comes into play when we talk integration. Okay, let's maybe do one example, 2 examples. We got 15 minutes. Find C that satisfies the mean value theorem for f of x equals x plus 1 over x on 1/2 to 2. Okay. Is this a continuous function on 1/2 to 2? Yes. Is it differentiable on 1/2 to 2? Yeah. Is both continuous and differentiable on the interval? So the mean value theorem applies. So now I have to figure out how it applies. Well, we need to find a point in the interior that has the same slope as the secant line, right? So we want to solve f of 1/2 minus f of 2 over 1/2 minus 2 equals f prime at c. Which is f of 1/2 is 2 plus 1/2 is 5/2. So this is minus 1, right? Equals f prime at c. No, that's not true. Sorry. I want 0. Hang on. Okay. F of 1/2 equals 1 over 1/2 plus 1 over 2. And f of 2 equals 1 over 2 plus 1 over 1/2. And so these things are equal. This is 5/2. 5/2. So I want 0 equals f prime at c. We good with that? And f prime of x equals minus 1 over x squared plus 1. We want that to equal 0. So we want 1 over x squared equal to 1, which is x squared equals 1, which is x equals 1 or x equals minus 1. Right? And in this interval that we're looking at, we want x to equal 1. Let's look at this graph. This is at 5/2. This is 2. So our graph's going to kind of look like that right now. Good. Tangent line, secant line. So one of the questions has us prove that if P is a polynomial with roots at C1 and C2, there's a critical point between C1 and C2. What does this mean? Sort of graphically, what would you sort of draw for your picture here? Yeah. If the polynomial hits there and there, right, and it's a polynomial, polynomials are continuous and differentiable everywhere. So they satisfy the mean value theorem, right? So I don't know how it gets from there to there. Maybe it has more roots in here, but it has to go back to here. So the secant line between those 2 points is the x-axis, which means that somewhere between there, you're going to have a derivative of 0, right? It might have a lot of derivatives of 0, but at least one place it will have a derivative of 0 between any 2 roots. So that's basically just sort of a turning point theorem. Like you have to turn around between roots, basically. How would you do this? Show f of x equals x to the 4th plus 3 x plus 1 has exactly one root, or sorry, exactly one root between -2 and -1. Maybe I should say in that interval. How would you do this? Take the first derivative, okay, and then do what? Okay, so you got 4x cubed plus 3 is f prime. And so on a number line, if I would solve this, I would have the only real root of that is here at negative cube root of 3/4, right? And that's less than -1, right? Or I guess closer to 0 than -1, so it's bigger than -1, right? We all good with that? Okay. This is the only critical point for f. If there was more than one root in here, then it would have to satisfy Rolle's theorem, right? And you'd have to have some place where the derivative was 0 in there. If there was more than one there would need to be some critical value, critical point in that interval with f prime equal to 0. It's not, there's not. So there can be at least, at most one. One root. How do I know there's at least one? Have we shown that there are roots in an interval before? Sorry? Yeah, that looks kind of difficult with this to solve that x to the 4th plus x cubed, or 3, x to the 4th plus 3x plus 1 is equal to 0. What's some way that we can say that we have a root there, but not actually find it? I think this was chapter 2 stuff, maybe beginning of chapter 3 stuff. Probably. The y value switches from positive to negative. You remember what that theorem's called? It's another value theorem, but it's not the mean value theorem, it's the intermediate value theorem. F of -1 is going to be -1 to the 4th. Plus 3 times -1 plus 1, which is going to be, that's a +1, that's a +1, that's a -3, that's -1. But f of -2 equals -2 to the 4th plus 3 times -2 plus 1. That's going to be 16. Minus 6 is 10 plus 1 is 11, right? So it switches from negative to positive inside that interval, so we have a root in there. Okay. Questions on that one? So we have 1, we have exactly 1 because the derivative is never 0 in there, so you have exactly 1 root between -1 and -2. Okay, I will put up a, well, I'll put up these videos on Canvas, and we'll talk more about 4.2 stuff again tomorrow. That homework's not going to be due until next week, but you guys can get started on it. All right? Yeah, because we have spring break, fall break, don't we? It's fall break this weekend? Is that Monday and Tuesday? Yeah, so it'll be due Wednesday, not Monday. Okay, yeah, good. Yeah, I don't know if you guys have fall break, but we do. Okay. All right, so you get Monday and Tuesday off here, but then you get Tuesday and Thursday off, or Thursday, Friday off there. Fine. Oh, will it let you? Okay. I'll try and unlock it. Send me an email if I forget. Remind me to.